Hello, good day. I am Giovanni Entero, but you can call me Gio. Today, let's learn together something new and something useful when it comes to resource management. But before that, you might be wondering why there are a lot of stuff in my first slide, from parabolic curve to exponential curve to logistic curve to boat to different types of fish, including the different stages of their life cycle. Anyway, all these things relate to my presentation today. And actually, I'm pertaining to these concepts: maximum sustainable yield, or MSY, maximum economic yield, or MEY, maximum social yield, or MSCY. And actually, a little caveat, I was tasked to discuss only the first two concepts, but I decided to include the third one because actually, the one is the improvement of the other one. What I'm trying to say here is that from MSY, it is improved to MEY, and then from MEY, it is improved further to MSCY. Now, I've already mentioned that all these concepts are actually very useful in resource management, but the question is, how can we apply these concepts? Now, stay tuned and find out the answer all throughout my discussion. So for now, let's go to my presentation outline. So first, we will be discussing or introducing something, a brief introduction, but actually I will just talk here resource management. And the second one is important definition. And basically these are definitions of the three concepts I've presented to you on my title page. And the third one, since we are talking about here management, what if I'll differentiate management and development for a specific resource? Okay. And the most important one is the theoretical and graphical presentations plus critique of MSY. And lastly, the references. So now let's proceed to the brief introduction. Resources management. Why do I have to talk about resource management here? As I've said, those three concepts are very useful when it comes to managing resources. Now, what comes to your mind if you hear the word resources? Well, most of you will think that resources pertain to all of the things that we can find on Earth that can be utilized for a specific purpose. And that's right. And when we talk about management, it's actually a system or a process that aims to attain a certain or a specific objectives or goal. So basically, when we talk about resources management, it is a critical aspect of any project or organizational operation involving the efficient and effective deployment and allocation of resources to achieve specific objectives. It encompasses various types of resources, including human resource, financial resource, natural resources, including food, fishes, trees, animals from the wild, etc. And also, to manage human take from the wild, one needs to know how much can be safely taken without depleting the resources one wants to take from, and without otherwise negatively impacting the environment. Because the mindset of human is that once there are available things, they will take as much as they want, without considering the fact that with their actions or with their doings, that actually can harm the population stability of a certain resource they are taking. Now, going back to the first bullet, the key there is specific objectives, or shall I say policy objectives. Now, if your policy objective is more of maximizing the production or yield, then there will be a corresponding concept for that. Now, if your goal is to maximize economic benefit, then there's also a corresponding concept for that. Now, if your goal is more of social consideration, like providing or generating employment opportunities for the unemployed ones, then there will also be a corresponding concept for that. And later on, all throughout my discussion, you will realize what those concepts are. And since we're talking about management here, as I've said, I'll be differentiating about to you later what's the difference between management and development for a specific resource. Okay, basically, I will be talking here fishery management. For now, let us have some important definitions, which is actually the second section of my presentation outline. Okay. So we'll be starting with what is maximum sustainable yield. So it can be called as maximum surplus production, maximum equilibrium catch, maximum constant yield, maximum sustainable yield, sustainable catch. Now, in our language as math major, when we talk about equilibrium, it is actually a point or a condition that if it is stable, then any disturbances or perturbations, the system will always go back to that point. Otherwise, if it is unstable, then it is not that significant on the system. It is the maximum catch that a population can support, provided that it is sustainable, meaning we can continuously get that much harvest without compromising the ability of the future to get that much of harvest too. It is the highest theoretical equilibrium yield that can be continuously taken from a stock under existing average environmental condition. And I will be explaining that further later. And I just want to quote this. It is the highest catch that's still allows the population to sustain itself indefinitely through somatic growth, spawning, and recruitment. For the case of fishery management, that's why I presented to you the different stages of life cycle of fish, because all those stages actually influence the population of the fish. Okay, next. What is maximum economic yield? So basically, when we are talking about maximum economic yield, we are very concerned here with the cost and the profit. So the level of catch and associated level of fishing effort that maximizes the profits of the industry over time and on a sustainable basis is actually the main concern of maximum economic yield concept. So here, we're just actually talking about the catch and associated level of fishing effort that maximizes the profit. Next one is the theoretical greatest difference between total revenues and total cost of exploiting a fish stock under existing environmental conditions and where inputs are valued at their social opportunity cost. So meaning to say, given a maximum catch allowed, if our effort is less than the catch, then that means that we are just under exploiting the resource. If our effort is greater than the catch, meaning to say we exert a lot of efforts, but our catch is not increasing, then that's a sign of unhealthy population and maybe that's a result of overexploitation. Now, if our effort is equal to the catch, then we have no gain at all. Meaning to say, if we are talking about maximum economic yield, we have to remember four things: the effort, the cost, the revenue, and the profit. Next, it is equal to the maximum resource rent. So if you're not familiar with resource rent, you can think of it for now as a profit, although there are important differences of resource rent and profit, but in our case, we can think of it as a profit for now. And it is realized at a level of fishing effort, which is below that one which produces maximum sustainable yield. This is what I'm trying to say recently, that actually MEY or maximum economic yield is just an improvement of maximum sustainable yield with consideration to maximizing the economic benefit. Okay, next is what is maximum social yield? A social consideration. So, for example, improvement of socioeconomic conditions of small scale fisher folks, because actually MSCY or maximum social yield is very applicable to small scale fisher folks if we are talking about fishery management. And it could also be generation of employment opportunities for those unemployed ones and improvement of the income distribution matter. And it can be thought of as a modification of the maximum economic yield to account for non-purely efficiency aspects, example, poverty and distribution. That's why I keep on saying that maximum social yield is just an improvement of maximum economic yield by taking into consideration social aspects. In my point of view, it would be best to call this as maximum socio-economic yield rather than maximum social yield, because actually we're considering here economic factors and at the same time social aspects. So a combination of social and economic. So it must be socio-economic yield, something like that. But I don't know why they call it maximum social yield. It's up to them. Next is the one most applicable to small-scale fisheries, as I've said. And this is the level of catch and corresponding effort which provides the best possible solution to social problems given the policy objectives and all possible alternatives because it considers economic and social aspects. So I think that's it. I hope you get the point or the definition of those three concepts because that's the most important thing today before we proceed onto theoretical presentations of those concepts. But for now, let's move to my third section of my presentation outline, the management versus development. So here I'll be citing a specific resource, which is fishery. So I'll be talking here fishery management versus fishery development for clarity purposes. So when we talk about fishery management, it is a pursuit of certain objectives through the direct or indirect control of effective fishing effort or some of its components. So say for example, minimum mesh size. We can actually institute or enforce this for the purpose of regulating the size of fish capture and increasing the productivity of the resource. Because if the mesh size is small, pwede nating makuha yung mga fingerlings at saka fry. And we are actually giving a delay in the regeneration of the population size in the coming generations. If the minimum mesh size is relatively big, then we are safe. And also, we can enforce system of licenses. Like we will not allow anyone to access a certain location for fishing if that person or people has no license to do so. Next is fishery development. So it is the expansion of effective effort through a set of assistance programs for the purpose of attaining certain objectives. For example, quote unquote subsidized. For example, subsidizing motorization for the fisher folks for the purpose of exploiting the underexploited resource and increasing fish supplies and fisheries income for the case of fishery management. So it's like we are giving opportunities for the other fisher folks to explore the unexploited area and let them get more income. And it can be expanded broadly to improvement in post harvest technology, expansion of fishing effort, marketing and transportation of fishery products, provision of infrastructure and other facilities, and many more. So I hope you get the point of what is the difference between fishery management and fishery development. So the bottom line here is fishery management is thought to be required once a fishery becomes overexploited. And that's the usual mindset of everyone else. We tend to impose now rules once we see something wrong in that thing. And fishery development is thought to apply while a fishery is still underexploited. That's what I'm talking about recently. And the general objective for both is the attainment of optimum rate of exploitation of the fishery. But the question is how to define this optimum. So if the policy objective is to maximize the fish production, remember what I've said in my introduction, it pertains to maximum sustainable yield. That's the equivalent concept for that. And if the policy objective is to maximize economic benefit, then that's maximum economic yield. If the policy objective is more of social considerations, generation of employment opportunity, improvement of income distribution matter, etc., then that will be maximum social yield. So as I've said, from maximum sustainable yield, it is improved to account economic benefit to maximize economic benefit, and so it will become maximum economic yield, and it is further improved to account social aspects, and now it is maximum social yield. So I hope you get the point or the idea of these concepts. So now we will proceed to the most important part of my presentation, the theoretical and graphical presentations plus critique of MSY. But before that, allow me to go to my next screen so that I can demonstrate to you or explain to you clearly what are the meaning of these things in theoretical settings and also in graphical settings. Okay, let's go. Hello, welcome to my other screen. So first, remember the time when I told you you must be or we must be cognizant about how much resources we can take from a source without inducing instability to the population. So actually, when we are studying the three concepts that I presented to you earlier, we cannot escape population dynamics. So now we will begin our theoretical discussion at population dynamics. And you know what? In studying population dynamics, hindi tayo makakatakas sa exponential growth model because ito yung pinaka-basic among the population dynamics model. And actually, the other model usually derived from exponential growth model. So here I presented to you an example of exponential growth model in the form of differential equation. So this is actually a differential equation. So if you're not familiar with differential equation, don't concern yourself too much for that. But for the purpose of this discussion, I'll be presenting to you this kind of model. So in this model, makikita nyo na may R tayo dito. R actually represent the intrinsic growth rate, and N here actually represent the population size, and T here actually represents the time. But remember, the N, the population size, is actually a function of time. Meaning to say, we can write n in the form of n of t, and we can interpret this one as varying as the time goes by. So now the most important thing here is to know the figure or the graph of this type of model. So actually, the figure equivalent to this model is of the form like this one. So if we have this xy plane, something like that, or any plane you want, the behavior of this model is actually like this, a J form. Meaning to say, it increases without bound because of this arrow. Meaning to say, it is not constrained by any limiting factors. So, kung iisipin natin, if you're going to model human population, this model is very unrealistic because human population is constrained or limited by a lot of factors. Say, for example, the availability of food, water, and a lot more things. So, meaning to say, we can't use this one to model population of human. So, a lot of researchers try to improve this model, accounting those limiting factors in a more simple and systematic way. But before that, why do we call this one as exponential growth? Because if we are going to solve that one, we can actually obtain a solution of this form, n0 e to the rt. And remember that e here stands for exponential. That's why we call this one as an exponential growth equivalent to this model. So now, going back to the improvement of this exponential growth model, accounting for the carrying capacity or the limiting factors in the environment, then we can have this logistic growth model. So logistic growth model actually derived from exponential growth model, because if we are going to simplify this one, we can obtain something like this, dn over dt, and then distribute this term to here and here, so we can have rn minus rn squared over k. And actually this term is actually the exponential growth model. So that's what I'm trying to say to you, that some of the population dynamics models are actually derived from exponential growth model. And one example of that is the logistic growth model. And actually logistic growth model is the foundation of maximum sustainable yield model. That's why I want to discuss this one to you in detail. So now, other parameters have the same definitions as exponential growth model, except for the k. K here denotes the carrying capacity. Although it is just a single value, but it accounts for the limiting factors in our environment. Actually, this is the main driver of population growth. If we are going to think of it, the interplay between reproductive success and mortality. And later you will see what I mean during the time I said reproductive success and mortality when we are going to illustrate this one using its corresponding graph. So without further ado, let's illustrate this one using its corresponding graph. So we're actually approaching to MSY. As I've said, this is the very foundation of maximum sustainable yield model. So we must try to understand this one thoroughly before we can understand the maximum sustainable yield model thoroughly. So here, this is actually the equivalent graph for the logistic growth model. It is in S shape compared to the exponential growth model in J shape. Meaning to say, if it's in J shape, it is not constrained by any limiting factors, while if it's in S shape, it is concerned by some limiting factors. And in our case, it is represented by the K, the carrying capacity. So how do we interpret this graph? So as you can see, at an early stage, the graph is not that steep, meaning to say the population size is slowly increasing. So it can mean that there are only few individuals who are capable of reproducing. But as the time goes by, the population size is rapidly increasing, meaning to say there are a lot of individuals who are now capable of reproducing. But observe that when the population size is approaching the carrying capacity, the growth slows down. So meaning to say, in this area, the competition is intense. The competition for available resources, for example, food, water, sunlight, is intense, and up to the point that birth rate is equal to the mortality rate. That's what I meant when I said the reproductive success and mortality actually the driver of population growth. And that's what I've meant during the time I've said the interplay between reproductive success and mortality are actually the driving force of population growth. If the mortality is equal to birth rate, there will be no growth in population. And that's the time when the carrying capacity is reached, meaning to say the competition is intense for the available resources. So here we are actually visualizing the graph as population size versus time. We are tracking the population size as the time goes by. But what if we are going to view this one as growth rate versus population size? Meaning to say, we are assuming that the only factor affecting the growth rate is the population size. So what am I trying to say here is, remember at the early stage, the population size is small, meaning to say the growth rate also is small. So in this curve, equivalently here in this portion, the growth rate is not that fast. And at this point, the population size is rapidly increasing, meaning to say the growth rate is increasing. And this point actually is equivalent to this part, where the growth rate is rapidly increasing and so the population size is increasing. And in this part, the growth of population size is slowing down and is actually equivalent to this portion. So meaning to say we can view this graph as this one. So what am I trying to say here is that for growth rate at an early stage, we are providing the resource to grow at their maximum ability or the 100% growth rate. But if the population size is approaching the carrying capacity, the growth rate slows down because, as I've said, due to intense competition and the birth rate is equal to the mortality rate. So to make it clear, what I'm trying to say is like this one. At an early stage, the portion of this graph is equivalent to the portion of this graph. At the latter stage, the portion of this graph is equivalent to the portion of this graph. And during the time the population size is rapidly increasing, the growth rate also is rapidly increasing, which is actually equivalent to this portion. So that's how we translate the population size versus time to growth rate versus population size. So now let's move to the maximum sustainable yield, which is actually our topic. And as I've said, when we are talking about maximum sustainable yield in managing resources, we are actually pertaining to the harvest or the amount of resources we are actually taking from a source. So we have to account that quantity we take out from the source, and that is represented by the added component here, H, or the harvest rate. How often, how fast, how much resources we harvested from a source. So this portion of the model is actually the logistic growth curve. That's why logistic growth model is actually the foundation of the maximum sustainable yield model. We just added a component H to account for the amount of resources we take from a source. Now we are already familiar with this kind of graph, but why there is K over 2 here? How do we get that point? So remember the logistic growth curve of the form dTRN 1 minus n over k, which actually represents the population size over time. And we can get this point by actually differentiating this population size with respect to time also and equating the result to 0. So in doing so, if you're not familiar with differential equations and differentiations, then you cannot appreciate the process of getting that point or getting that quantity or number. But for the purpose of this presentation, I would like to demonstrate to you how to get that one. So to get that one, we just have to differentiate this one and equate the result to 0. In doing so, we have d over dt, dn over dt. And since this one is equal to this one, so we have d over dt, Rn, which is actually this term, 1 minus n over k. So after differentiating, we can obtain a term of the form r equal to 2Rn over k. So now we are going to multiply both sides by k over 2r, multiply in this part, and then in this part we have to multiply also the same quantity, k over 2r to 2rn over k. So here we can cancel out r, and in the right hand side we can cancel out k, we can cancel out 2r. So the remaining quantity will be n equal to k over 2, or we can write this one in a nice form as n equal to k over 2, which is actually this quantity. So in the language of mathematics, we actually call this one as inflection point. An inflection point is actually a point where the curve changes its concavity. By saying concavity, I mean concave downward or concave upward. So for this case, from this point to this point up until the inflection point, the graph is actually concave upward. And from this point to here, the graph is actually concave downward. So this point is the determining factor where the curve is actually changing its concavity. And similarly for this case, as I've discussed, this portion here is actually equivalent to the portion here, meaning to say the point of inflection here is actually equivalent to the topmost part of the parabolic curve. So I hope that's clear to you now. So here, as you can observe, from stack size, we change it to yield, and from time, we changed it to stock size. So actually in resource management, they don't use the population size, but rather the stock size or the available size of resources. And yield here actually pertains to how much catch we can have given the stock size. Now going back to H, how do we interpret that one? So how do we interpret the harvest with respect to maximum sustainable yield concept? So for example, we want a harvest of this much. So for example, we call this one as H1. And another case is we want a harvest of this much, and we call this one as H2. Another harvest here, we call this one as H3. So how do we interpret the different harvest rate? So for the first one, we have actually two equilibrium points. So the meaning of equilibrium points, as I've said in my previous discussion, is that a point, if it's stable, the system will always go back to that one. So meaning to say, in this case, the equilibrium point here, if we harvest along this curve, the population size will not change. So for example, given this stock size, the yield we get is this much. much. So we're actually inducing no changes in the population size. So another case for H2 is we only have one equilibrium point. And compared to this one is much higher. Here, we don't have equilibrium point, meaning to say, if we harvest of this much, then we are actually introducing instability to the population. So what am I trying to say here is that, for example, going back to H1, if we harvest of this much, then the population size remain. Now, if we have a stock size of this much, then supposedly the maximum harvest or yield that we can have is this much, but we only harvest this portion. So meaning to say the remaining population here will go here and will make the population size increase. The same case if we harvest of this much and we only take this much, so the remaining population here will add to the previous population size, and so that will make the population size increase. So intuitively, if we harvest below the curve here, we are giving room for the previous population to increase or to grow. So for example, nag-harvest tayo outside the curve. So for example, this case here, and we take this much. So meaning to say, this portion will be deducted from the population size here. So whatever the population size in this portion will be reduced by this amount. So meaning to say, the population size is reduced. We are introducing changes in the population size in the form of reduction in the size. Every time we harvest outside the curve, whatever quantity outside the curve, that quantity is equivalent to the quantity that will be deducted on the prior population size. So that's totally opposite if we harvest below the curve. So I hope you get the point. So the bottom line here is if we harvest along the curve, the population size will remain the same. Meaning to say, the quantity that is added to the population is equal to the quantity that we harvested. So for example, we have a pond like this for the case of fishery management. Whatever quantity that is added to this one, and then we take it equal to this quantity. So we are not actually introducing changes to the population. The population size remains the same. However, if we harvest below the curve, then we are giving the chance the population size to grow more, to increase more. And if we harvest outside the curve, we are actually reducing the population size. That's the idea of maximum sustainable yield. Now, the question is, saang parte ng curve to harvest provided that it is sustainable? To answer that question, the first case is, remember that if we harvest along the curve, we are not changing the population size. So we can repeat this one all over again up to certain periods and the population size remains the same. So that is sustainable. If we harvest below the curve, we are giving the population size to grow more up until it reaches the curve, up until it reaches the carrying capacity. So it is also sustainable. So meaning to say, the portion of this graph where we can harvest sustainably is this portion here. But question, there is some portion here that is outside the curve. Remember that if we harvest outside the curve, we are reducing the population size. But if the population size reaches this curve, this part of the curve, then it will stop reducing. So meaning to say, the entire curve is actually our equilibrium. If we harvest along the curve, we introduce no changes in the population. So that's an equilibrium point or an equilibrium state. So question, what is the portion of the figure that if we harvest that much, we can harm the population, or in a worst scenario, we can deplete entirely the population size? So to answer that question, this portion here, if we harvest this portion here, we keep on decreasing the population size. So remember that if we harvest this portion here, we are not touching the curve, this curve. So meaning to say, we continuously reduce the population size, and if we continue to do that one, we can eliminate the population size of a certain resource, in our case, a fish resource or a fish population. So to recap, if we harvest below the curve, we are giving the population size to grow more. If we harvest along the curve, we are not changing the population size. If we harvest outside the curve, then we are introducing changes in the population size, but the portion that is sustainable to take our harvest from is this portion of the figure, and the portion of this figure where the harvest is not sustainable is this part here. So I hope you get that one. So now, why it is called maximum sustainable yield? So compare to all of the portion of the graph, what is the maximum part? Well, technically, this part is the maximum. And we know that if we harvest along the curve, it's sustainable. And since it is along the curve, it is sustainable based on our explanation a while ago. So, meaning to say it's maximum, it's sustainable, it corresponds to the yield. And so, this point here is the maximum sustainable yield, or the MSY. So I hope you get the point of maximum sustainable yield. So it is actually the highest theoretical equilibrium yield that can be continuously taken from a stock under existing environmental condition. So in fishery management, fishery needs to be regulated to sustain for stocks and a profitable fisheries. Because the thinking of human being is they can harvest and harvest and harvest to gain more money, but they are not thinking about sustainability. So it is important to know the concept of maximum sustainable yield. So I hope you get the point of maximum sustainable yield. And the good thing here is that if we know the carrying capacity, the value of the carrying capacity, we already know the maximum sustainable yield, which is actually equivalent to K over 2. So for example, hypothetically, if the carrying capacity value is equivalent to 100, then we can say that the maximum sustainable yield is 100 divided by 2, or that's 50, something like that. So that's why this is very useful in studying maximum sustainable yield, which is actually derived from the point of inflection of the graph. So now, leading towards MEY, or maximum economic yield, so here we are actually now considering the maximum economic benefit. As I've said in my earlier discussion, we are talking here about revenue, cost, effort, and profit. So here I just presented again the logistic growth curve and the corresponding parabolic curve before we can talk about MEY for comparison purposes. So don't worry, the pink line here stands for the cost without subsidies. So here we are now accounting the cost. But before that, let me explain the change in the labeling of the axis. So from stock size, we change it to effort. So this is very different. So as I've said, if we have this much of harvest, and if we harvest this much, the remaining population will be added to the existing population size, and so we are giving the population size chance to grow more. But here the situation is different because it's effort. As you can see, yield and value are directly proportional. If the yield is increasing, the value is also increasing, so we have no problem for this one. But the stock size, or the population size versus effort, are inversely proportional, meaning to say, if the effort is increasing, the population size, or the stock size, is decreasing. So I hope you understand that one. If we exert more effort catching the fish, then we are actually reducing the population size or the stock size of a certain fish, something like that, in fishery management. So I hope it's clear to you. So since we are accounting here economic benefit, as I've said, profit, so we can think of this curve now as the total revenue curve. So it's different from this curve because this curve is actually the yield, and this one now is actually the revenue curve. So that's slightly different. So now here we are assuming that the corresponding cost for effort is actually linear, which is actually represented by this pink line. So again, when we are talking about effort, this pertains to, for example, how much time you are spending in fishing, how many of you are fishing, how advanced your techniques are, how advanced your equipment are. Those things have underlying cost, and those things represent effort. So assuming that it grows linearly, so it is represented by this pink line. So how to interpret this one? So in my previous discussion, MEY is obtained below the MSY. So for example, this is the cost. So anything under this one represents the cost. And since we are treating this curve as revenue curve, anything under that curve is our revenue. So to get the profit, total revenue less the total cost. So meaning to say the remaining area is this one, and this represents the profit. So that's our concern in maximum economic yield. So now, in terms of profit, compared to MSY in this portion, this is actually smaller than this one. So meaning to say, this portion is larger than this one. So in terms of profit, we can gain more profit in this portion than in this portion. So how to prove that one? So observe the difference here. If we talk about marginal cost, the difference is very small, but the increase in cost is a little bit large. So meaning to say, if we continue to do that, we can have profit loss. So compared here in this portion, the value is large, but the cost is small. So meaning to say, we can exert more effort to gain more profit. That's why we elevated this one up to this one. And this portion actually is the optimal position for us to have a maximum profit. So profit pertains to economic, And so in this portion is the portion for maximum economic yield. That's simple. So it's obvious that it's actually an improvement of MSY by accounting the economic aspect, specifically the profit, the revenue, the cost, the value, and the effort, something like that. So I hope you get the point of maximum economic yield now. So what else? So you can see there is a portion here, a block portion, the intersection between the parabolic curve and the linear representation of the cost. This portion actually represents the portion where the value of the catch is equal to the cost of fishing. So you can gain no profit at all. So careful of this one. So now what if the government provides subsidies for fisher folks to fish a lot more, and so the corresponding curve will be look like this one. And so considering the thinking of human beings, they have advanced equipment subsidized by the government, for example, they will fish and fish and fish and fish and exert more effort and more effort and more effort without realizing that they reach this point and they think that can give them maximum profit, but not that actually. That makes the situation more worse. So as you can see here, this one is still larger than this one. But as I've said, the thinking of human beings, they will fish a lot as long as they can without considering, for example, sustainable practices. And then they reach this break-even point and starting to lose their profit. So that's the very idea of maximum economic yield, considering the cost with subsidies and without subsidies. So now in most fisheries, maximum economic yield is actually obtained with even less fishing effort. As you can see here, the effort here is on the left of the effort in attaining the maximum sustainable yield. So aside from that advantage, less effort compared to this one, but higher profit. So that's what I'm trying to say, that maximum economic yield is obtained with even less fishing effort, but larger profit. So simply because the linear decline in cost is steeper than the corresponding decline in catch near the peak of the parabolic curve, the thing that I've explained to you in this part and in this part. So unfortunately, effort in most fisheries in the world is above the MSY level, resulting in low catches and economic loss. This is possible since the government gives subsidies, and that's what I explained to you with this curve. So that's actually a trap. Since they are being subsidized, they tend to overfish because it requires only a minimal effort for them to obtain more and more catch without realizing that at a certain point they will reach the break-even point and they will start losing profit. So that's the very idea of MEY, or maximum economic yield, with the assumption of linear cost with subsidies and linear cost without subsidies. So I hope you get the point. I really want to make a lot of talks about this one, but we are constrained with time. So the bottom line is the maximum economic yield is the antidote to the illusion of most fisher folks and some politicians as well who keep on giving subsidies without realizing what are the effects of that one, that higher fishing effort results in higher profits. But based on my explanation, it's not always the case. So in reality, profits decline once effort exceeds the MEY, or maximum economic yield level, and catches decline once effort exceeds the MSY level. So be aware of that one, especially if you are in fishery management or resource management in general. So I hope you get the point. So lastly, for the maximum social yield, as I've said, it is just an improvement of maximum economic yield by considering social aspects. So here, as I've said, anything under this curve, this pink line, which represents the cost of fishing. So the cost will pertain to the wages given to the fisher folk, something like that, and the cost, say for example, the gasoline, the effort, or anything that has underlying cost that will be accounted in this area of the curve. And anything under this red curve is the total revenue less by the cost. The remaining ones are the profit. So for this case, up to this point, we have been concerned with models which attempt to maximize catch, or the MSY, actually in aggregate economic surplus, or MEY. Now, what if we opted to do social considerations? For this case, MEY will be modified, as I've said, by taking into account social factors. Say, for example, generation of employment opportunities for the unemployed one. So as you can see here in this portion, although there's a little bit more effort than MEY, but at least in this portion, the additional effort is actually intended to give job opportunities to the unemployed ones so that they can gain income to sustain their family or to sustain their needs. So technically, MSCY or maximum social yield cannot be made independently without MEY and MSY. So as I've said, maximum social yield is supposed to be called as maximum socioeconomic yield because it's actually an improvement of MEY or maximum economic yield. So the additional effort there is actually the effort that gave to, for example, generation of job opportunities. That's the only additional effort for that one. And meaning to say, aside from accounting the economic yield, it accounts also the social aspects. It's a little bit better than economic yield, accounting only the economic benefit but not the social aspect. So MSCY is also better. So it's an improvement of MEY once again. So the bottom line is MSCY or maximum social yield take full cognizance of the likely conflict between income and employment objectives. More employment lead to overfishing, for example, like that, and a reduction of the aggregate fishing income. For small-scale fisheries, employment objective has more weight for the purpose of distributing income fairly to lower income groups. As I've said, MSCY accounts for the effort of providing job opportunities to those, for example, unemployed ones or low income groups. So that's actually a slight improvement of maximum economic yield. So I hope you understand the difference or the idea of maximum sustainable yield now, maximum economic yield and maximum social yield. The most important thing here is that maximum social yield is the foundation and it is improved to account for the economic benefit and it is made to maximum economic yield, and maximum economic yield is improved to account for social aspects and it is now maximum social yield. That's actually their relationship. Again, maximum social yield cannot be made in the absence of MEY or MSCY. So I hope you get the point. So that's it for the theoretical and graphical presentations of the three concepts, the MSY, the MEY, and the MSCY. So now it's time to go back to my main screen and discuss the critics of MSY. So let's go. Hello, welcome back to my main screen. So we are done with the graphical and theoretical presentations of maximum sustainable yield, maximum economic yield, and maximum social yield. So now it's time for us to go over to the critic of MSY. So why do we have to present only the critic of MSY? Because as I've said in my discussion, that this is the foundation of the three. The other two are just the improvement from this one. So I'll just make it quick. So here it goes. We will be starting with number one. MSY cannot be determined for a stock unless overexploited. So this is one of the downside of MSY because you are allowing first the population of a resource to be exploited first before you can detect MSY. And number two, MSY and the optimum fishing effort cannot be predicted in early stages of developing fisheries, and stock assessment should focus on detecting it as rapidly as possible. That's what I'm trying to convey in the first item. And number three, once MSY is detected, fishing effort should be reduced up to 30% in order to achieve sustainability because in the first place, you are allowing the population to be exploited first. And once you detected the MSY, the effort will be reduced up to 30%. And number four, the assumption of average recruitment and average environmental condition may lead to wrong advice in highly fluctuating stocks because it's very rare for a certain fish, for example, or a certain resource to have a stable population. So they are very dynamic, they are very variable, meaning highly fluctuating. And number five, the dependence of MSY on size at first capture and age structure in the stock is ignored. As you can see before in our presentation of the model, that's very simple. That is made very simple, but at least it captures the dynamics of a certain population of a resource. But if you're familiar with law of parsimony or parsimonious theory, the more simple the model is, the better, as long as it captures or it mimics a real life scenario. And that's what our model was. Because if we add a lot of factors to account, meaning to say we're adding parameters, and so the tendency is in the long run, we tend to overfit something. And 6 MSY is achieved by setting limits on fishing mortality, but as a different fishing gear select and target different species, and some other species are not targeted at all. So meaning to say MSY is not that effective if the source has multi-species. For example, in fishery management, if your pond, for example, has a lot of species, then MSY is not always simultaneously attained. And number 7, MSY is rarely attained simultaneously for all species within an area. That's what I've said when I cited a pond with multi-species. MSY cannot always be simultaneously attained. And lastly, number 8, the model is too simple to capture the whole dynamics of the population. Always put in your mind the law of parsimony or parsimonious theory. And I just want to say to you this, no model is perfect, no model is correct. Some of those models are just useful enough to mimic a certain dynamics or a certain scenario in real life. And that's it. So these are just some of the critics of MSY, and maybe there are still more, but let's stop at number 8. And I think that's it. So we'll move now to my references. So these are my references. If you wish to read a lot about the topics I've presented to you, the three concepts, the MSY, MEY, and MSCY, you can browse these references. And thank you. Thank you for your time. Thank you for listening. Arigatou gozaimasu. Bye bye. See you in my next video about lakes.